In this chapter, we're going to discuss the design options that an application programmer chooses from. In particular, we'll start with the architectural choices, and service-oriented architecture is one. So service-oriented architecture, SOA, it's a collection of distributed components, and they provide or consume services. Also associated with an SOA architecture is something called the Enterprise Service Bus, an ESB. An ESB supports discovery for consumers. We talked about discovery. Uh, Providers must register with the ESB so that they can be discovered. And the communication between providers and consumers is provided by the ESB, as is protocol translation if the producer and consumer use different protocols. So here's a pictorial representation of that. Hopefully you can see it with the different colors. This comes from Wikipedia. Uh, and any consumer can talk to any provider and vice versa. And any protocol translation is performed by the ESB. So producers and consumers in SOA are standalone entities, and they're deployed independently, so they could be anywhere. Components have interfaces that describe the services they request from other components and the services they provide, so they have explicit interfaces. Service can be implemented in whatever language and technology is most appropriate. So there's no requirement that languages or technologies be uniform across the services in an SOE. And we'll see that in microservice architecture as well. So why would you use an SOA? Historically, you used an SOA because microservice architectures hadn't been invented yet. Now, SOA still has a use, and it's more in terms of integration of systems. So, for example, suppose you're a bank and you just acquired another bank. You now have two copies of all of the software that banks use: loan management, fraud detection, account management, and so on. Each of these systems has its own user interface and process assumptions. So how do you integrate them? You integrate them using SOA. So you would create a uniform database for accounts and loans, maybe the same as one of the banks, maybe different from both the banks. You would attach the new databases and the legacy databases to the ESB. You would attach the legacy systems to the ESB. You would write translation mechanisms that you would put in the ESB to translate from the original bank specific formats to and from the new uniform database format. So it's possible that the components in the SOA are managed by different organizations. That was the original motivation behind it. What additional elements are required if the producer and consumer components are managed by different organizations? Develop a use case for SOA that's different from the banking example. Again, these discussion questions should be dealt with offline. Now let's move to microservice architecture. So around 2002, Amazon promulgated the following rules for their developers. All teams will henceforth expose their data and functionality through service interfaces. And software services must communicate with each other through these interfaces. And then somewhat redundantly, there will be no other form of inter-process communications, no direct linking, no direct reads of another team's data store, no shared memory. And these are all techniques that were used within Amazon prior to the introduction of microservice architectures. The only communication allowed is via service interfaces over the network. And it doesn't matter what technology the services use, and that's borrowing from SOA. Amazon described microservice architecture as SOA done right. You can take that or leave it. So the basic packaging unit of a microservice is a service. And services are independently deployable. What that means when you have independent deployment is that if you want to call them, you have to find them. They have to be dynamically discovered. So the mechanisms for discovery would be DNS if you're using virtual machines, ESB if they're attached to an SOA, or a service mesh if they're microservices and they're containers and they're managed by some orchestration system. Microservices communicate only via network messages, and network communication is inherent in microservice architecture. You have independently deployable services that consequently have to communicate via messages. Uh, and message communication takes longer than in-memory communication. But it's not a coincidence that microservice architectures date from around the time when cloud computing became available. And cloud computing enabled fast network communication. The fact that you can use any technology avoids a great deal of errors. So a common cause of integration error is version incompatibility. You're using version 3.2 of the library. I'm using version 3.3 of the library. It's possible that those versions are incompatible. So let's remove the requirement that we agree on a version of the library before we begin development. You can use 3.2, I'll use 3.3 because we're only communicating with messages, it doesn't matter. And this independence allows each team to independently choose their implementation language. You can choose to implement in Java, I can choose to implement in Python, for example. And the libraries, as I said, can be independent. And I don't need to coordinate with your team. My team doesn't need to coordinate with your team, which saves time because coordination is expensive in terms of time. You have to, in order to coordinate, you have to decide an agenda for the coordination. You have to have some mechanism for coordination, either a meeting or some sort of web-based communication. You have to record your decisions and then you have to adhere to them. So there's an expense associated with coordination among teams, and microservices removes that expense. Amazon has a two pizza rule. Every team can be fed with two pizzas. And in practice, this rule limits the team size to roughly 7 people. At one point, I presented this to a German automotive company, and a big guy was sitting in the front. He says, "You mean if this means I have to work alone?" But in general, we're talking about 7 people in a team. And if the service grows so that 7's not enough, then you divide the service into 2 services, which then have to be staffed appropriately. Each microservice is owned by a single team. Again, reduces coordination needs among teams. If I shared the ownership, then I'd have to coordinate with another team. If my team shared the ownership of a microservice with another team, then I'd have to coordinate with them. Since my team has the exclusive ownership of the microservice, I don't need to coordinate with anybody in terms of making changes or deploying it. On the other hand, it may be that that microservice doesn't keep my team busy, in which case I can own multiple microservices. Again, the fact that I'm having limited coordination means that I may not trust my other teams. They may have gotten the contract wrong. They may send me an incorrect interface. Possibly they've been hacked and I wouldn't be aware of it. And so I use defensive programming. So I check the interfaces for the interface parameters for validity. I require a security token to be passed in Kerberos as an example to manage the security requirements. So again, offline discussion questions. compare microservices and SOA with respect to the ownership of components. Remember, in SOA, it's possible for different organizations to own the components. Is that true in microservices? And what's the relationship between microservices and APIs? So in order to call a microservice, you have to have knowledge of its API. So what does that mean? Now let's do a little more analysis of microservice and their qualities. So you can analyze the microservice in terms of its quality attributes: availability, modifiability, performance, reusability, scalability, and security. And we'll talk about these individually. So if an instance of a microservice fails, it'll be detected by the load balancer, or maybe the autoscaler, which is a portion of the orchestrator, assuming that it's packaged as a container. And the load balancer knows the instance has failed because the instance is supposed to report that I'm alive periodically. And then once the load balancer detects it's failed or thinks it's failed, it doesn't send any more requests to the failed instance. And then the autoscaler will recognize the fact that an instance has failed, and it may create a new instance depending on the rules that you have. The availability depends on state. So if the microservices are stateless, or if the microservice is stateless, then a failed instance can be replaced just by creating a new one. You have a launch specification that specifies what the characteristics of a launched container or virtual machine are. You maintain that. You know the launch configuration for the service that failed. You launch another one. If the microservice keeps state, then the state that's involved in it will fail, will be lost. And so you need to have some mechanism to recover it. And this depends on where the state is stored. You could store it in the client, you could store it in a database, you could store it through a shared memory model, even though microservices aren't supposed to be using shared memory. But that's you will see that microservices ought to be stateless, and the reason for that is availability. Modifiability. Okay, so the measures of modifiability are coupling and cohesion, and it's enhanced by having low coupling and high cohesion within a single service. And we've known that for since the 70s. And if a single service provides a single function, then cohesion is likely high. Coupling depends on the overlap between the function performed by the service and functions performed by other services. And if coupling is high, then you can refactor to reduce the coupling. Microservices depend on network traffic. A network message will take longer than a memory message. And so if you want to compare the performance of a system implemented as microservices with one implemented in a less distributed fashion, it really is going to come down to how many messages must be sent in the microservice design. But there are things you can do to improve the performance of microservice design, including caching, save values. You need to make sure that the cache is up to date when you do that, but that will improve the performance. You can send messages in binary rather than text form. We'll get back to that. And you can co-locate the services that have high rates of communication. So if service A is going to send a message to service B and we put them on the same physical processor, then it doesn't need to go over the network. And so how about reusability? Well, in order to have reuse, you have to locate common functions and isolate them in a single service. And so that means you have low fan out among the services. You end up having a deep service tree rather than a shallow service tree. And it means that more services are involved in satisfying a single request, which means more messages are involved in satisfying a single request. Scalability depends on if adding a new service increases the cost linearly or sublinearly. So scalability is really a cost issue. And this depends on how the cloud provider charges you. Usually, if you add a new instance of a stateless microservice, then you're increasing the cost linearly and not more than linearly. Uh, you want to worry about security again because you may not trust the clients. And so you would use HTTPS instead of HTTP. Now, of course, there's a trade-off involved in terms of time. You would apply patches promptly. So we will talk about patches and patch management in another lecture. You want to get rid of unused resources because it's a security problem if you have there's something called VM sprawl where you create a virtual machine and you forget to delete it. And VM sprawl may lead to security problems because then it wouldn't be updated and an attacker could infiltrate that and potentially get credentials. There are examples of that happening. You do not write any security sensitive code such as password managers. They're very difficult to write, takes strong expertise, and things like that are best used as independent services written by people who are security experts and have tested, and the password manager has been used by others. And you don't embed credentials into either codes or scripts. So again, some discussion questions. What's the trade-off between performance and reusability in microservices? What's the trade-off between modifiability and performance in microservices? Now let's look at microservices and containers. So microservices communicate only with messages, and containers are accessible only through network interfaces that are intended for message-based communication. So it seems like it's a fit, and it is. So a pod is a collection of related containers that are deployed and scaled together. So you would say that two containers are in the same pod, and that would mean that when they get deployed by your orchestrator, that they would be deployed together onto the same host. And the services that make up a platform as a service or a service mesh, there are ideal candidates to be collected in a pod with the microservices. And placing the platform service resources near the microservices, and near is a fuzzy term meaning in the same rack or in the same data center. Uh, uh, and if you do that, that will reduce the latency of messages. And containers are small. Microservices are small. And so, again, it's a reasonable fit. Now, how do you do discovery? Well, virtual machines are awkward. Let me say that a different way. Containers come and go fairly quickly, uh, especially if they're being load balances. DNS is not a service that was designed for quick removal and creation of services. And so that's typically done now by the orchestration service, and the orchestration service has a discovery service, and it has some sort of container that acts as the phone book for the individual instance of a microservice. So let's suppose that the microservice wants to call a logging service. Well, if you deploy them together, then that call is going to be quick. Now it turns out that logging service may get deployed a copy of that logging service may get deployed with other with other microservices. And so your discovery service, when you ask where is the logging service, should only give you back the logging service that's been deployed with you. So you have to manage the discovery services to keep requests local. Same thing's true for canary or A/B testing. You tell the discovery service which microservices instances are involved in canary testing, and it will route the user request to the appropriate places. But again, that knowledge can be local if your canary user population is localized in some way. Geographic localization is done as a way of canary testing, for example. You can also localize in terms of language, in terms of region, or sort of other user visible attributes. And the orchestrator can populate the discovery system with the specialized microservices that know about localization. So here's a list of microservices that can be bundled together and they can be bundled together in pods, but they need to be discovered by the service mesh. Configuration, distributed coordination, logging, I talked about that, tracing, various metrics. If you're going to have a dashboard, alerts, things like that. So you need to be conscious of the bundling aspects of putting things in pods. You need to protect against failure. Remember the long tail? The more Essentially, the more messages it takes to reach a service, the more likely is the messages will get lost along the way, either through failure of one of the intermediate services or through a network failure. And so how do you protect against that? Well, there are a couple techniques, assuming that things are idempotent. So remember what idempotent means. Uh, you can make bridged requests or hedged requests, I'm sorry. Make more requests than you need, and then cancel the requests or ignore the responses after you get a certain number of responses. Or you can do the same thing really in a different way. So you issue 10 requests, and then when 8 of them have been satisfied, you issue 2 more. So now you have 4 requests outstanding. And then after 10 total requests have been satisfied, you can cancel the unsatisfied request. Again, this assumes that it's idempotent if the request actually you're going to change something, like add a number to a database field, then that may happen multiple times, and that would lead to inconsistency of the database. So discussion questions. Why is configuration of service recommended for inclusion in a pod? Is it possible to have a microservice without managing the microservice and containers? What are the trade-offs involved in doing this? So now let's move to communication. So that's the architectural choices that a designer makes. Now let's move to communication. So there are 3 different things we'll talk about in terms of communication style. There's RPC, remote procedure call. There's REST, representational state transfer. And there's query and an API. So remote procedure calls allows code on one host to call a procedure on another host, just as if it were local. And it has 4 elements: the IP address of the recipient, the name of the target procedure, uh, the version number of the target procedure, and an untyped data block that has the data that you want to send arguments. So the basic steps for most RPC implementations are: you write a package definition to define the software interface. And a package definition file looks like a standard procedure declaration with parameters or specified types. And then you have an RPC compiler that looks at that static definition and produces stub code for the call. So when you want to send a message, first you link together the stub, the program, or the RPC runtime system program, the stub, the RPC runtime system all together to make the client module. And on the server side, you link in the server stub, the server routines themselves, and the RPC runtime system. Now your call can call a procedure on another node by the client can call the procedure on another node by using its modules, and the server can interpret. It'll get sent to the server, and the server can interpret. So remote procedure call creates what's called a strong contract. Both the sender and the recipient have to have agreed on the parameters and the types of the parameters, and which message will be implemented by the service and how these procedures will be numbered. RPC requests can be either stateful or stateless. A stateful request depends on previous requests. For example, you must first open a file before you can write to it. A stateless request does not. So I talked about failure and state previously. The options for message transport is typically TCP or maybe TLS if you want worried about security. And some RPC implementations use a post request to send the request and response. REST, so the basic issue that motivated the development of REST, or the basic development that motivated the development of REST, was the World Wide Web. If you have to have and the World Wide Web is fundamentally a collection of clients and servers. If you have to have a strong contract between the client and the server, that means that each client is bound to the server, and the server can only accept requests of a particular type. And so that motivated the development of REST, representational state transfer, which allows looser coupling. So first of all, in REST, the requests are stateless, and there's no assumption in the protocol that any information is retained from one request to the next. So you can retain state, but that's through agreement between the client and the server, and the protocol doesn't know about it. The information is exchanged is textual. So the web was supposed to be heterogeneous. There are lots of different types of computers out there with different representations of numbers and so on. And so using a textual specification makes it possible doesn't works with the heterogeneity, I guess is a way to say that. And REST is essentially get, put, post, and delete. Okay, and so each element is self-describing by labeling it with a MIME type, so that the receiver knows how to interpret the data. And it's used typically with HTTP or HTTPS. So RPC is, if you're worried about performance, you would use RPC. And it supports a programming style that allows distributed services to be called just by local services, but they're not terribly interoperable. So REST is intended to be interoperable so that your clients can interoperate with the server with a very loose type of contract between them. And so you can have independent evolution of clients and servers. So suppose, for example, that you have RPC between the client and the server, and then the server wants to change its interface. Well, all of a sudden, all of the clients have to change as well. Whereas with REST, the service can change its interface, and if it's appropriately implemented, then the clients don't have to change at all. And so both are used extensively in RPC, in microservice-based terms. RPC is used in the parts of the system where the interactions between services are well understood or where performance is a priority. REST is used in external, when you have external facing services and the clients, and in areas that are changing. So you can change the client without having to change the server and so on. There's also something, so the thing about REST is that it's potentially high bandwidth, sends a lot of information because the server doesn't know what the client wants. If your client is an edge device, if it's a smartphone or an IoT device, it may not be able to handle all that bandwidth. And so Facebook, Meta, developed something called GraphQL, which really doesn't have anything to do with graphs, so the name is a little bit misleading. And this says you have an explicit type statement of the data that might be provided by the server, and that's called the provider schema. And the client has an explicit statement of data that it wishes to receive, the client schema, which presumably is a subset of the provider schema. And so then the client sends a query in terms of the client's schema, and the providing service responds with a JSON. And we'll talk about JSON in a minute. And so it uses less bandwidth because the server responds only to the data that's requested. It doesn't, so in general, the REST service doesn't know the client needs and will provide all the data that it has. On the other hand, if you want to make up a query, you can't do that with GraphQL because you have to have the explicit schemas, whereas REST allows a lot more flexibility in terms of ad hoc queries. So discussion questions again. Could the World Wide Web have been developed using RPC? And how does the World Wide Web manage state communication between services if you're using REST, and REST is stateless protocol? Now let's move to structuring request and response data. So you have to package the data that you send, whether you're using RPC or REST. And there are three common protocols that we'll talk about: XML, protocol buffers, and JSON. So XML is extendable markup language, and it adds annotations, tags, to a textual document. And the tags specify how to interpret the information in the document by breaking the information into chunks or fields. So in HTML, which is a form of markup language, you would say this is a paragraph. So XML is a meta language, and it allows you to define a customized language to describe your data. And your customized language is in turn defined by an XML schema, which is an XML document. So HTML is a markup language. XML is designed for data transferred between services. HTML is is used to describe the layout of web services. But if you are familiar with HTML, you'll see what the tagging is all about. The trouble with XML is that you have to scan the whole thing. And one of the questions is, why is that? And so parsing an XML document takes time. And that led to the development of JSON, which we'll talk about in a minute. But first, I want to talk about protocol buffers. And protocol buffers provide a specific syntax for the package definition file. Remember that when you're using RPC, so protocol buffers are used in conjunction with RPC. Remember, when you're doing RPC, you have a package specification file. And this defines the structure of the untyped block. So RPC had an untyped block where the data was, and a protocol buffer says how to interpret that. And they're usually used in conjunction with gRPC, which is a binary form of RPC. So remember that everything was text in the web because it was heterogeneous. If you're going to start doing binary transformations, then A, It's going to be shorter. Think about the representation of the number 236 in binary versus in text and how many bits it takes. And secondly, you're assuming that the endpoints both have the same representation. So that if I send binary data, that both of them are going to be big endian or little endian, if you know what that means. And the data types and protocol buffers are close to programming language data types, making marshalling and unmarshalling efficient. So marshalling means how do I take the data in my program and put it into a message, and unmarshalling means the reverse. How do I take the data in a message and turn it into my program? And protocol buffers simplify that. So now I have services written in different languages, and it becomes difficult to communicate between those services. Well, protocol buffer solves that problem. So you would place your protocol buffer in a .proto file. So that's the specification. And there are language-specific compilers for .proto file. So the language-specific compiler translates the file into code that marshals, unmarshals, and sends messages. So for example, if you want to communicate between Java and Python, then the compiling the .proto file with the Java protocol buffer compiler will get you a Java procedure. Compiling it with the Python protocol buffer compiler will get you a Python procedure. But the two procedures understand the same messages in the same format. And now the two services can communicate using the procedures generated by the two language-specific proto compilers. A virtue of protocol buffers is that you have an explicit schema. So having an explicit schema lets you detect errors in type and just in general lets you check the interface before the message is sent. And so that lets you detect the error earlier. And another virtue of explicit schema, which XML has as well, is that you can save the schema in a database. And now you can search that database to see which variables are used by which services. And the list of protofiles or the content of the protofiles has to be up to date, or your service doesn't work. And so having a list of up-to-date services gives you an idea of the documentation of the architecture, gives you a document describing the interfaces of the architecture. One of the problems with architecture documentation is keeping it up to date. This makes it, explicit schema makes it automatic. And then finally, we want to talk about JSON. So JSON has nothing to do with Java. That's the first kind of comment to make. And it structures the data as name value pairs or as array data types, which are programming language specific. And it's independent of any programming languages. It says it's not big, has nothing to do with Java. It's a textual representation, but it has no schema. So all you do is send name value pairs, and the client and the server have to agree on the interpretation of these name values. So XML requires reading discussion question, reading in the entire message before marshalling can begin. Why is that? And JSON can perform marshalling as the message is read in. Why is that? And that's the end of this chapter.